Unit 8 Notes 2 Part 2. It's about mirrors and their reflections. We're going to talk about different types and shapes of mirrors and how they reflect differently. So, of course, we all are familiar with a flat mirror. I'm sure most of us look at a flat mirror every single day. Um, and basically, the image in a flat mirror is going to be a virtual image. So, what do I mean by that is, let's say we're taking a look at through a mirror and we're taking a look at this object right here, this chess piece. The red one represents the real object, the real thing, but in the reflection, we're actually, our eyes are focused as if we're looking at something on the other side of the mirror. So we have a virtual image right here. Um, Keep in mind that there's no light that travels along this path because, like, on the opposite side of this mirror, you probably have like a wall or something. So it's just like it's an optical illusion kind of thing where you have a virtual image that appears on the opposite side, and that's how your eye focuses it, and even though the object is right in front of you. So the outgoing light rays from the object always diverge, but they always converge. They go back to your eye. So you can see here from the top of let's take a look at the top of this chess piece. The light rays are actually diverging. There's two light rays that are coming from the top, but they're bouncing off the surface of the mirror and then converging back into the eye. So they come back to a single point when they get to the eye. So all the points, it's not only the top and the bottom, but literally every single point on this object that you can see is doing the exact same thing. The light rays are diverging, meaning they're separating, and converging back, meaning that they're coming back together. All right. Virtual images in a plane mirror are inverted. That's going to be true for every single type of virtual image. A virtual image is always inverted. So what do I mean by that is that if we were to have someone go up to a mirror and lift up their right hand, the reflection looks as if they're lifting up their left hand. So it's going to be backwards. And you can do this by just showing like text in a mirror. You know that text always appear backwards in a mirror. So virtual images, just once again, in a plane mirror are always going to be inverted. This is why a lot of emergency vehicles like fire trucks and ambulances and police cars, the front of them has written on what type of vehicle it is. Like if it's a police car, it would say the word police on the front, but it would be backwards. And the same thing with this ambulance truck. The ambulance truck here has the word ambulance written backwards because when you're driving, you're looking through your rear view mirror, and your rear view mirror is going to be producing a virtual image. So when the virtual image is showing you the reflection, it's actually inverted. So you're reading the word ambulance correctly in the mirror. But of course, we know that not all mirrors are going to be flat. I'm sure you've been to one of these like fun houses or I think there's one in the Mall of America, like a fun mirror maze or something like that, where you can go and see different reflections and kind of play around with mirrors to get crazy optical illusions of things that don't actually exist. And this is because these mirrors are curved. So if you've ever seen like the side profile of one of these, they're curved in different directions to kind of show you different types of reflections. So we're going to talk about one specific type of shape of mirror, and that is a concave mirror. Let's talk about the word concave first. The word concave, it basically means that it's going to curve inwards or cave in. That's the way I like to remember it. Concave, caves in. So like we have this mirror right here, it's curving inward. And so the surface of the mirror curves inward. We've already mentioned that. And there's also two specific points I'm going to mention during this lecture. We have the focal point here, and then this C point, which is the center of curvature. I'll talk about that in a second. But the focal point right here, that's the most important one. That's the point where light waves reflect or refract and combine together. Okay, so any single light ray that comes in contact with this mirror, if it's coming in straight like this, anywhere that it bounces off of this mirror is going to bounce off, and all of them are going to pass through this focal point. It does not matter where on this on the mirror it would hit. It would actually have to go through the focal point if it was coming in straight. So if light ray is parallel to this one, like these two are, these are parallel. If they're coming in, hit the mirror, always go through the focal point. Now this point over here, this is called the center of curvature. Some diagrams label it 2F, and the reason why they call it 2F and this being F is because the center of curvature is a point that is twice the distance from the mirror than what the focal point is. So let's say we're measuring the distance between this point right here in the mirror and this point right here, the focal point. And let's say this distance was 5. That means that the center of curvature to the mirror would have to be 10. All right, so there is a significance to this point just besides that it's twice the distance. And we'll talk about that in a second here. But just keep that one point in mind, the 2f or the center of curvature. Here's a little diagram to show you what a curved mirror can do with different colors of light. So we have a green ray, a red ray, and then a blue ray. And then what they're going to be doing is bouncing off of the mirror and then hitting the focal point. So you can see here, this bounces off straight and then comes out this way. There's the focal point. Green bounces off here, goes through here, and then blue does the same thing. It bounces off here and then comes in here. And of course, like we discussed before, when we mix all 3 colors of light, we get the color white. So you can actually see that there's a white point right there, and that's the focal point. All right? So the center of curvature, like we mentioned before, this point that is double the distance of the focal point. There is a little bit more to that, so we'll talk about that in a minute. So that was, in concave mirrors, they always produce what's called a virtual image, like we've discussed before. And you know that a virtual image is going to be the inverse image. So if I'm lifting up my right hand in a mirror, it's going to appear that my reflection is lifting up their left hand. So the thing about the virtual image here is that it's magnified. Okay, so the virtual image is going to be bigger than what appears to be in the actual reflection, right? The only instance where we get a virtual image is if the object is within the focal length of the mirror. So if we are in between the focal point and the mirror, then we will produce a virtual magnified image. So I'll show you an example here in just a second. All right, so here we go. We have object distance is less than the focal length. So let's say this is our mirror, this curved line right here. And then this is our focal point right here. If the object is in between the mirror and the focal point, what's going to happen is that the light waves from the object are going to hit this mirror, and they're going to diverge and hit this focal point like this. And then let's say this one hits here, and because it didn't come in straight, it's actually bouncing off. This one's not going through the focal point. It's actually bouncing off like this. Right, so this is that same principle that we talked about, that if this angle of incidence equals the angle of reflection. So we've mentioned that before. This angle of incidence is the same as the angle of reflection. So the arrow is going this way. Of course, if we were to continue this line and this line going forever, you can see that they're actually spreading apart, so they'll never intersect. Where would they intersect, however? On the opposite side of the mirror. So we're drawing an imaginary line. This line does not exist. I want to emphasize that. This line does not exactly exist, but we're drawing like an imaginary line. And same over here, we're going to draw an imaginary line here. Notice that they do intersect here. So what's going to happen here is that that's where the object is going to appear. It's going to appear that it's on the opposite side of the mirror, just like with a flat mirror. The only difference here, though, is that now the object looks a lot bigger. So you can see here that if we are in between a focal point and the concave mirror, we're going to get a virtual image, but it's going to be magnified. Virtual image created, upright, and magnified. So with a concave mirror, there's actually multiple different scenarios that we can have when it comes to different reflections. So this type of mirror will create what's called a real image if the object is located beyond the focal length away from the mirror. So we already discussed what happens when we're in between the focal point and the mirror. We get a virtual image. But what if we're past the focal point? If we're past the focal point, we get something called a real image. And a real image is the image of the object where the outgoing light rays from an object converge on a single point, just like this. The way you can remember a real image is that it will appear to be upside down, but it will not be inverted. So if you were to show a word in a mirror and get a real image, you would still be able to read that word, but it would be upside down. So like it wouldn't be inverted, but it would be upside down. I'll show you a demonstration here, a little interactive, to kind of demonstrate how that looks. But basically all you need to know is that uh, when you're past the focal point, you're going to get a real image. So here is our interactive with a concave mirror. So let's say we have this object. We can select different objects like a candle or an arrow, but I like using the letters A, B, C because it actually shows you what happens to the letters. They actually become backwards. So like we discussed before, if we're in between the focal point and the mirror itself, we will get a virtual image just like this, and we will be magnified. The reason why we're magnified is if we do a thing called a ray diagram where we kind of show which way the rays are going. Let's say we have this one that goes perfectly straight, and any line that goes perfectly straight is going to go through the focal point. I can't stress that enough. Any line that goes perfectly straight and hits a concave mirror will always go through a focal point. Then we're going to draw one that doesn't go perfectly straight. Let's do this one. It actually hits the center, and when it bounces off, it's going to bounce off at the same angle that it came in. So the angle between this red line and this gray line over here is the same as the angle between this red line and that gray line. So it's going to bounce off. And then you draw your imaginary lines like we discussed before, and that's where the top of the object is going to be. So you can just see really quick. I'm going to turn these off. You're going to get a magnified image. That's a virtual image when you're in between the focal point and the mirror. What actually happens when you're on the focal point? Well, actually, you don't get an image whatsoever. It tells you that it goes on forever, but it gets to the point where you can't actually see the image, so you don't get an image there. If you're beyond the focal point, you start to get a real image. Okay, so a real image is going to occur here, which is upside down, but you can still read it. Right, and then if we're in between the focal point and the center of curvature, which is this 2F, you would get a magnified image. This is magnified because it's bigger. If we're exactly on the center of curvature, you get an image that's the exact same size. And then if we're past the center of curvature, you get a reduced image. So you get an image that's much smaller. So right there's a center of curvature that's the same size. In between the center of curvature and a focal point, you get a magnified real image, and then over here it would be reduced. Just to show you one more time with these rays turned on, this is what happens with these rays. So you can just kind of follow along here. Alright, so let's continue back to the notes. So just to re-emphasize one more time here, you have the object distance is greater than the focal length, you'll get a real image, so an upside down image. All right, so light waves, yep. So this is a great example that you could do even at home. You can get a spoon from your drawer in your kitchen and then actually see virtual versus real images. You would have to get very, very close to the spoon itself to get a virtual image, and that's to the point where you could only see like a little portion of your face, maybe even just your eyeball. But basically, the spoon itself, being a concave reflective surface, is a great representation of how you can see a virtual and a real image. So if you wanted to, you can go to your pantry or your kitchen cabinet and grab a spoon and just see the difference between the virtual and the real images. So you can see here that the person taking this picture, this is a real image because they are upside down. So if it appears to be upside down, it's always going to be a real image. Here is a drawing. This is not a picture, this is a drawing. The way I know this is because if this was a picture, then it would be a picture of someone holding a camera, but this is someone's artistic representation of what a real versus virtual image looks like. So this is a real image, and what I want you to notice here is that everything is going to be upside down, and then different points look kind of distorted, and that's definitely going to happen with a curved mirror like this. And then this is going to be a virtual image where it appears to be right side up. So I'm just showing you this to show you what the difference is. All right, so let's move on to a different type of mirror called a convex mirror. This is going to be less complex than a concave mirror. A concave mirror is probably the most complex mirror, but a convex one is actually pretty simple. It's a convex mirror. It's the exact opposite shape. So what I mean by that, it doesn't curve inward, it curves outward. It reduces the size of the image, but allows you to see more area around the mirror. So this is why oftentimes you'll see them in like corners of stores like this. This is because probably for like security reasons, so that people can see different people around the store. Oftentimes you'll also see small convex mirrors on the side of people's side mirrors on their cars, and that's to get their blind spots so that they can actually see the blind spots. Sometimes even like bike mirrors, you can have a mirror on your bike that will be a convex mirror that allows you to see more. Right? These side mirrors on a car are actually slightly convex mirrors. They appear to be flat, but they do have a little bit of curvature. That's why they always say on the side of them, objects in mirror are closer than they appear. Because going back to this point right here, it reduces the size of the image. It makes things look smaller. And naturally to us, when things look smaller, they appear to be further away. So this is why they have this little warning right here. Objects in mirror are closer than they appear. Because they appear to be pretty far away, but it turns out they're actually pretty close. So this type of mirror only creates virtual images. This is just the same thing like a flat mirror, where it only produces virtual images. It does not produce any real images. And then, like I mentioned before, objects in mirror are closer than they appear because all the reflections are going to be reduced. They're going to appear to be smaller. All right, so this is how it works. So let's say our arrow here is going to be the thing that we're going to do our reflection. So we have a light wave and a divergent reflected wave. So if you have a straight line that comes in, I mentioned before, any straight line is going to want to hit the focal point. So on the opposite side of this curve, we're going to imagine that there's a focal point. So the reason why we have this arrow, let's stick to this arrow only. The reason why we have this arrow going this way is because actually, if we were to draw this out like a dotted line, it would go through the focal point right there. And this one is just going to rebound off the surface and then come out at the same angle, just like that. And then obviously these two yellow lines are not going to be intersecting anytime soon. So on the opposite side, this one's going through the focal point, and then this one is going to intersect it right there. So that's where we're going to draw the top of our object, just like that. So we get a virtual image that's created and it's smaller. Here's a little review for this notes. We're going to finish up here, but this is the last kind of graph that I made, like a graphic organizer. We have 3 different types of mirrors: flat, convex, which you just covered, and then concave, which I think is the most complicated. Will a flat mirror ever produce a real image? No. Convex? No. Will a concave mirror produce a real image? Yes. In fact, it's the only one that could produce a real image. But it can also produce a virtual image. And there's differences there. So for the real image, for the concave, the object is past the focal point. But for the virtual image, the object is in between the focal point and the mirror. And then the reflection size, in a flat mirror, it would be the same. In a convex mirror, it would be reduced. And then in a concave mirror, we have magnified, same, and reduced. So we have 3 different possibilities for sizes. And I made another little graphic organizer to kind of show you what happens in different spots. This looks a little bit complicated, but it's actually pretty easy. Imagine this curved surface is our mirror. This is an imaginary line running down the center, so we have our focal point and then the center of curvature, this 2F. If we are in between the focal point and the mirror, we have a virtual image that's magnified. On the focal point itself, you don't get an image. It's kind of like it just looks really blurry. Between the focal point and the center of curvature, you get a real image that's magnified. On the center of curvature, you get a real image that's the same. And beyond the center of curvature, you get a real image that's reduced. So it's going magnified, 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 and then reduced. This final slide is showing you 2 different images to show you 2 different representations of real versus virtual and reduced versus magnified. So in the top image, anything in the red portion is going to be a real image, so anything beyond the focal point, and virtual is going to be between the focal point and the mirror. Reduced versus magnified is going to be anything between the center of curvature and the mirror is going to be magnified, and anything past the center of curvature is going to be reduced. So this relationship up top is showing you what type of reflection you would have, and then this relationship down here would show you the size of that reflection. So that concludes Notes 2. What we're going to do now is work on the practice problems for Notes 2. So see you in that video.